Let us go through this tomorrow's portion of yesterday's class, which was not properly recorded or possibly not properly viewable. We are starting with the different varieties of nozzle itself. Nozzles are used in power plants to supply steam jet to the turbine blades at high velocity and with high velocity at the expense of high pressure induced in the turbine itself. There is a phenomenon defined as the stagnation. There is a phenomenon defined as stagnation of the fluid flow. Now, this stagnation properties, what is the definition of stagnation procedure is the isentropic stagnation state is defined as a state of fluid which is flowing, which is in flowing or in motion, would reach where it is brought to rest isentropically by steady flow, adiabatic, and 0 watt output device. Or we can explain like this: say a fluid is flowing, and and if it is brought to rest isentropically, means without any heat exchange between the fluid and the surroundings in steady flow, adiabatic, and 0 watt output device. In a device, we are supposed to stop this fluid flow as isentropically, which where the flow was steady, means the fluid flow is not variable in time. It is flow rate is not variable in time. Adiabatic, there is no heat transfer takes place between this vessel. Means it's completely sealed from outside. No heat is coming in and no heat is going out from the fluid, and there is no sort of work output is getting. We are making to stop this particular fluid at a particular instant. Then, if we can stop this fluid, we can brought to rest this fluid. Then we have to find out this process is known as stagnation point. So there are the pointers. We have to use the process to start to bring the fluid to rest, which is a which is a steady flow. Is like this. It is the fluid flow should be steady, means it does not change. It is rate of flow, it does not change with time. Heat flow should be adiabatic. If there is no exchange of heat takes place between the fluid and the surroundings, and there should not be no work done to stop this work. There should be no output from the fluid. So no energy is coming in and no energy is going out in terms of work done or in terms of heat. If in such a way, if we can stop the fluid, we can, that this process is called stagnation of the fluid itself. And the stagnation enthalpy, after the stagnation, what will be the enthalpy of the fluid is given by H with a suffix 0. And the temperature of the fluid at the stagnation point, it is equal to T by T with the suffix 0. Means H0, T0 is the enthalpy, and T0, enthalpy and temperature of the fluid at stagnation pressure. Now, what we are doing here, for an isentropic flow through a nozzle, so we are sending the fluid through a nozzle, and the flow is isentropic, means there is no heat exchange takes place from the fluid to the surroundings. In one sense, it is adiabatic too. But so that it says that H0, the stagnation enthalpy of the stagnation state will be equal to the H, means H of the enthalpy of the fluid at the flowing state plus V square by 2, where V is the velocity of the fluid. Actually, this is the kinetic energy of the fluid per unit mass of heat transfer. H0 is the enthalpy of the fluid per unit mass of heat per unit mass of the flow at the stagnation point, and H is the enthalpy of the fluid anywhere during the flow process, and per unit mass, and V square to the power V bar squared by 2, where V bar is the velocity of the fluid at that particular point under consideration, maybe at the exit, and it's it is a vector, so it is resident with the V bar, and mass mv square by 2 is equal to V square by 2 because the m is equal to unity itself. Now, the stagnation process enthalpy is not changing. When fluid is brought to rest with in a from when fluid was flowing in a steady flow, which was brought to rest and without in adiabatic process, and there is no work output is done during this stopping, then what you say that enthalpy at the stagnation stage is not changing at all, which is equal to minus V into dV, or dH is equal to V plus dV. And from the property relation of the fluid, of any fluid is given by T into ds is equal to dH minus V into dP. For isentropic flow, there is no ds takes place, so left hand side of term will be reduced to 0, and so dH is equal to V by dP. dH is equal to V by dP. Now, I'm sorry, dH is equal to dP by P, dP by rho itself. dH, here, I'm wrong, dH is equal to V into dP, which is again equal to dP by rho, because 1 by P is the specific volume of the fluid, specific volume of flow of the fluid, means the amount of fluid moving per unit time. So, isentropically flow, we know the change in enthalpy is equal to change in pressure divided by the flow of mass of the fluid itself. Now, if we use these two equations, this dH is equal to minus dV by dV, and equal with dH is equal to dP by rho, then what will happen? We replace dH by dP by rho, so dP will be rho minus rho V to the power V into then D into dV to the power V, or dP by dV to the power is less than equal to 0 itself. Why it is like this? And minus rho and V, therefore, will be negative, or it is less than 0. Why it is less than 0? Because it is negative. The change of pressure with respect to the velocity, in terms of the velocity itself, which will be less than 0, and which is negative, which change of pressure will go down with the increase in velocity. They are acting in opposite to each other. Change of pressure will reduce if the velocity of flow of fluid velocity is increasing. Velocity of flow increases. Therefore, the pressure decreases flow through a nozzle. The velocity increases and vice versa. If velocity decreases, the pressure will increase. The continuity equation thus gives omega is equal to rho into A into V. Omega is equal to volume of flow per unit second, equal to mass of the fluid, cross section of the fluid, and velocity of the fluid per second. And so mass of flow is equal to omega is equal to rho into A into V. By logarithmic differentiation, what will happen? We'll have d rho by rho, dA by V plus dV by V. Because if we take log on both sides, the log will be log omega and log omega plus log pi rho pi plus log V plus log V. And if we take divide, log rho, omega is a constant term, so it will be equal to 0. The rho will be, if we derive both these sides, it will be 1 by P into dP, 1 by A into dP, and 1 by V into V is equal to 0. So we can we can write this equation with equal to dA by P minus dV to the power D divided by V minus d rho by rho. Now, if we substituting from the equation 7 to 9, which tells us the value of dP is equal to minus rho into V to the power 3 bar into V to the power. So what is happened? We are putting the dV bar here. If we replace the d to the power V there, which means we have to put dP divided by minus dP divided by P into V to the power bar. So we are putting it here. It will be square because plus V is the square because there is already a V. This V will multiply with this V. So dP divided by d rho minus dP by rho, or dP by rho V 1 minus V square will go to the top, and the rho V square will go to the top. This rho will be cancelled by this rho, and V square into dP divided by dP itself, d rho divided by dP itself. D rho d by dV itself. diffuse. Okay. So, or dA by A is equal to dP dA by rho v square into 1 minus m square, because 1 minus m square, or dA, dA by A into m square minus 1 is equal to dV by V. Where m is less than 1, that is the inlet velocity subsonic. As flow rate A increases, the pressure decreases and the velocity increases. As the inlet velocity is subsonic, means m is equal to less than 1, means the velocity of sound is less than, our flow velocity is less than the velocity of sound. As the flow area increases, the pressure also decreases and velocity increases. And for the subsonic flow, a convergent passage means a passage whose cross-section area is maximum at the beginning and minimum at the end, and becomes a nozzle itself. And a divergent passage where cross-section area is less, minimum at the beginning and maximum at the end, which uniformly varies towards the length, becomes a diffuser. So convergent becomes a nozzle and divergent becomes a diffuser. Nozzle means which where it will reduce the pressure and increasing the velocity, and diffuser is increasing the pressure, reduces the velocity. When m greater than 4, which is for subsonic process itself, and for m greater than 1, which is supersonic inlet velocity, as flow area A increases, A decreases for a nozzle, pressure increases and velocity decreases. As flow area increases, when in case of diffuser, pressure decreases and velocity increases. For supersonic, a convergent passage is a diffuser, and a divergent passage is the nozzle. That's exactly opposite, because we say diffuser will decrease the velocity and increase the speed, increase the pressure, and as I mean this diffuser and convergent passage, and nozzle is it is speed increases and your pressure also decreases. Now what we have here, 4 sets of nozzle itself. The nozzle number A is the subsonic nozzle, where this is the type convergent nozzle. Here at the inlet, the area is maximum, and that area is gradually diminishes to the area at outlet where it is minimum. So in MAC, m less than 1 means velocity is less than velocity of the fluid less than the subsonic velocity. Then m1 will be equal to 0.2, and m2 will increase into 0.2. So velocity increases here and pressure also decreases. And the figure B is a subsonic diffuser, means where velocity reduces and pressure increases, where cross-section area A is minimum, 1 is minimum, and 2 is maximum, and it is varied. Where the Mach 1 is a 0.7 or less than 1, or is subsonic, then the Mach 2 will be again reduced to a considerable extent. Velocity will reduce further and pressure will increase further, as it is the acting as a diffuser itself. And M1 and input, there is another conversion nozzle where 1 the pressure in the area is maximum, and 2 the pressure area is minimum. If the flow is supersonic, means more than the velocity of sound, what will happen? The pressure will reduce. The velocity will as a convergent nozzle, velocity will go up and pressure will reduce. Thus, velocity which was less than 1 will go up to 2.4. For supersonic, it is more than the velocity of sound. It is more than the velocity of sound m. So it was already more than n. It becomes velocity becomes further increased, equal to 2.4, almost twice. M1 say 3, M1 was 2. It's comparatively reduced. It's because it acts as a subsonic diffuser. Here velocity is reduced. Initially was greater, equal to 1. Initially was outlet at rest, usually 2.4. Means velocity reduces and correspondingly pressure will reduce. Means although it is converging in the air, it is acting as a diffuser for supersonic speed. For supersonic speed, for this type of air where it is convergent at the end and divergent at the outlet, pressure is minimum at area is minimum at A, area maximum at 2, and which is similarly valid. The incoming speed is equal to the left is the supersonic, which is more than the velocity of 1, not less than the velocity of sound, which means m is greater than 1. So m1 will be 1.8. It will act as a this is as a converged nozzle where it speed increases from 1.8 to 3.2, and with the accessors with the drop of pressure here. So here it is, although the lowest lower area is at the left and higher the outlet. Inlet is the lowest and outlet is the highest. It is still acting as a supersonic nozzle itself. Now let us go to the critical pressure ratio and choked flow. Let us consider the isentropic flow of an ideal gas through a convergent dynamical row. So we are thinking if the gas is ideal, it obeys the perfect gas equation, and since PV is equal to MRT, it obeys this thing, and flow is isentropic as if